Imagine a world where machines not only process information but learn, adapt, and even surprise us with their creativity. What if the secrets behind this intelligence could be traced back to a handful of mathematical ideas? Today, we embark on a journey through the neural network revolution, a story of breakthroughs, setbacks, and the relentless pursuit of artificial intelligence. From the earliest sparks of inspiration to the powerful algorithms shaping our world, this is not just a tale of technology, but a glimpse into the future of human-machine collaboration. Our story begins in the late 1950s, when Frank Rosenblatt introduced the perceptron. Inspired by the human brain, the perceptron was a simple yet powerful idea, a machine that could learn to distinguish between different inputs. It was the first step toward mimicking the way our own neurons process information. The perceptron could recognize patterns, but its limitations soon became clear. Still, it ignited a wave of excitement, hinting at the possibility of machines that could truly learn. At its core, a perceptron is a mathematical model of a single neuron. It takes several inputs, each with its own weight, sums them up, and passes the result through an activation function. If the sum exceeds a certain threshold, the perceptron fires, producing an output. This simple mechanism allows the perceptron to learn by adjusting its weights, gradually improving its ability to classify inputs. But as researchers soon discovered, perceptrons had their limits. One of the most famous limitations of the perceptron was its inability to solve the XOR problem. XOR, or exclusive OR, is a simple logic function that outputs true only when its two inputs are different. Despite its simplicity, the perceptron could not learn this function because it is not linearly separable. This realization led to skepticism about the future of neural networks, and for a time, research in the field slowed. The inability of perceptrons to solve certain problems led to what is now known as the AI winter. Funding dried up, and many researchers turned their attention elsewhere. But beneath the surface, a few visionaries continued to explore the potential of neural networks. They believed that the key to overcoming these limitations lay in building more complex architectures, networks with multiple layers. The breakthrough came with the realization that stacking perceptrons into layers could unlock new capabilities. By connecting the outputs of one layer to the inputs of the next, researchers created multi-layer networks capable of learning more complex patterns. These networks could, in theory, solve problems that single-layer perceptrons could not. The stage was set for a revolution in machine learning. The key innovation was the hidden layer, a set of neurons sandwiched between the input and output layers. These hidden neurons allowed the network to transform inputs in complex ways, making it possible to learn nonlinear relationships. With hidden layers, neural networks could finally tackle problems like XOR, opening the door to a new era of artificial intelligence. Building multi-layer networks was only half the battle. Training them, adjusting the weights so the network could learn, proved to be a daunting challenge. Early methods were slow and unreliable, making it difficult to unlock the full potential of deep networks. Researchers needed a way to efficiently update the weights across all layers, not just the output. The answer came in the form of backpropagation, a clever algorithm that allowed neural networks to learn efficiently. By propagating errors backward through the network, backpropagation made it possible to adjust the weights of all layers based on the difference between the network's prediction and the actual result. This breakthrough transformed neural networks from a theoretical curiosity into a practical tool. Backpropagation works by calculating the gradient of the loss function with respect to each weight in the network. It starts at the output layer, measures the error, and then moves backward, layer by layer, updating the weights to minimize the error. This process, repeated over many examples, allows the network to gradually improve its predictions. The result is a network that can learn from experience, just like a human. A crucial ingredient in neural networks is the activation function. Without it, even multi-layer networks would be limited to learning only linear relationships. Activation functions like Sigmoid, TAN, and ReLU introduce nonlinearity, enabling networks to model complex patterns. Choosing the right activation function can make the difference between a network that learns and one that stalls. A typical neural network consists of an input layer, one or more hidden layers, and an output layer. Each layer is made up of neurons, each with its own set of weights and activation function. The network learns by adjusting these weights, gradually improving its performance on the task at hand. The architecture can be customized for different problems, from image recognition to language translation. The simplest type of neural network is the feed-forward network. In this architecture, information flows in one direction, from input to output, without any cycles or loops. Feed-forward networks are powerful for many tasks, but they have limitations when it comes to processing sequences or remembering past information. handle sequences and temporal data, researchers develop recurrent neural networks, or RNNs. Unlike feed-forward networks, RNNs have connections that loop back on themselves, allowing them to maintain a memory of previous inputs. This makes them ideal for tasks like language modeling, speech recognition, and time series prediction. Another major breakthrough was the development of convolutional neural networks, or CNNs. Inspired by the visual cortex, CNNs use specialized layers to detect patterns in images, such as edges, shapes, and textures. This architecture revolutionized computer vision, enabling machines to recognize objects, faces, and even emotions in photos and videos. Neural networks are hungry for data. The more examples they see, the better they become at recognizing patterns and making predictions. High-quality, diverse datasets are essential for training effective models, but with great data comes great responsibility. Ensuring privacy, fairness, and transparency is more important than ever. As neural networks learn from data, they can sometimes become too good at memorizing the training examples, losing their ability to generalize to new data. This problem, known as overfitting, is a major challenge in machine learning. Techniques like regularization, dropout, and cross-validation help prevent overfitting and ensure that models perform well in the real world. Training a neural network involves finding the best set of weights to minimize the error. This is done using optimization algorithms like stochastic gradient descent, ADAM, and RMSprop. These algorithms guide the network through the complex landscape of possible solutions, helping it find the best path to success. With advances in algorithms, hardware, and data, neural networks have grown deeper and more powerful. Deep learning, using networks with many layers, has enabled breakthroughs in fields like image recognition, natural language processing, and game playing. The revolution is just beginning, and the possibilities are endless. The explosion of deep learning would not have been possible without advances in hardware. Graphics processing units, or GPUs, are especially well suited for the parallel computations required by neural networks. Today, specialized chips like TPUs and neuromorphic hardware are pushing the boundaries even further, enabling faster and more efficient learning. One of the most exciting developments in neural networks is transfer learning. Instead of training a model from scratch, researchers can start with a pre-trained network and fine-tune it for a new task. This approach saves time, reduces the need for massive datasets, and allows AI to tackle problems that were once out of reach. Neural networks are transforming the way machines see and hear. In computer vision, they power facial recognition, medical imaging, and self-driving cars. In speech, they enable voice assistance, real-time translation, and emotion detection. These applications are just the tip of the iceberg, with new breakthroughs emerging every day. Neural networks have revolutionized natural language processing, or NLP. They power chatbots, language translation, and sentiment analysis, making it possible for machines to understand and generate human language. Recent advances like transformers and attention mechanisms have taken NLP to new heights, enabling models like GPT and BERT. Neural networks are not just for recognizing patterns, they can also create. Generative models like GANs and VAEs can produce realistic images, music, and even text. These models are opening up new possibilities in art, design, and entertainment, blurring the line between human and machine creativity. As neural networks become more powerful, ethical questions take center stage. Bias in training data can lead to unfair or discriminatory outcomes. Ensuring transparency, accountability, and fairness is essential as AI systems become more deeply embedded in our lives. The choices we make today will shape the future of artificial intelligence. One of the challenges with neural networks is their black box nature. Understanding how a network makes its decisions is crucial for building trust, especially in high-stakes applications like healthcare and finance. Researchers are developing new techniques for explainable AI, making it easier to interpret and validate the decisions made by neural networks. The trend in neural networks is clear: bigger models, more data, and greater computational power. Models like GPT-3 and AlphaGo have demonstrated the incredible potential of scaling up. But with size comes new challenges: energy consumption, environmental impact, and the need for smarter, more efficient algorithms. From personalized recommendations to fraud detection, neural networks are already woven into the fabric of our daily lives. They power search engines, social media feeds, and digital assistants, often working behind the scenes to make our experiences smarter and more seamless. While neural networks are inspired by the brain, they are still a far cry from the complexity of human cognition. Our brains contain billions of neurons and trillions of connections, enabling feats of perception, reasoning, and creativity that machines can only dream of. Yet, the gap is narrowing, and each breakthrough brings us closer to understanding both artificial and natural intelligence. Despite the progress, many challenges remain. Neural networks can be brittle, sensitive to small changes in input, and vulnerable to adversarial attacks. Making AI robust, reliable, and secure is an ongoing area of research, with implications for safety and trust in critical applications. Open-source frameworks like TensorFlow and PyTorch have democratized access to neural network technology. Researchers, students, and hobbyists around the world can now experiment, innovate, and contribute to the field. This spirit of collaboration is accelerating progress and making AI more accessible than ever. As neural networks become more important, education is key. Universities and online platforms are offering courses in deep learning, making it possible for anyone to join the revolution. The next generation of researchers, engineers, and entrepreneurs will shape the future of AI, building on the foundations laid by pioneers. The neural network revolution is not happening in isolation. Collaboration between computer scientists, neuroscientists, psychologists, and ethicists is driving new insights and innovations. By learning from each other, these disciplines are pushing the boundaries of what machines and humans can achieve. While much of neural network research has focused on supervised learning, new approaches like unsupervised and reinforcement learning are gaining ground. These methods allow networks to learn from unlabeled data or by interacting with their environment, opening up new possibilities for autonomous systems. Neural networks are not just tools for analysis, they are becoming partners in creativity. From composing music to generating art, AI is collaborating with humans to explore new forms of expression. The line between creator and creation is blurring, raising profound questions about authorship and originality. The neural network revolution is a global phenomenon. From Silicon Valley to Shenzhen, researchers and companies are racing to develop the next breakthrough. AI is transforming industries, economies, and societies, creating new opportunities and challenges on a worldwide scale. As neural networks automate more tasks, the nature of work is changing. Some jobs will disappear, others will be transformed, and new roles will emerge. Lifelong learning and adaptability will be essential skills in the age of AI, as humans and machines work side by side. Neural networks have the potential to address some of humanity's greatest challenges. From diagnosing diseases to fighting climate change, AI is being harnessed for social good. The choices we make today will determine whether this technology becomes a force for progress or a source of new risks. Despite their power, neural networks have limits. They struggle with common sense reasoning, long-term planning, and understanding causality. Researchers are exploring new architectures and learning paradigms to address these challenges, but many questions remain unanswered. The neural network revolution is far from over. As we continue to push the boundaries of what machines can learn, new discoveries and innovations await. The journey is filled with excitement, uncertainty, and the promise of a future where humans and intelligent machines work together to solve the world's greatest challenges. Looking back, the journey from perceptrons to deep learning has been marked by moments of doubt and triumph. Each breakthrough has brought us closer to understanding intelligence, both artificial and natural. The revolution is ongoing, and its impact will be felt for generations to come. At the heart of the neural network revolution are the people, scientists, engineers, and dreamers, who dared to imagine a different future. Their curiosity, persistence, and creativity have shaped the world we live in today. As we look to the future, it is this human spirit that will continue to drive progress. The next chapter of the neural network revolution is unwritten. Will machines achieve true understanding? Can we build AI that is ethical, trustworthy, and aligned with human values? The answers will depend on the choices we make and the paths we choose to explore. The adventure continues, and the possibilities are limited only by our imagination. As we close this exploration of the neural network revolution, one thing is clear: curiosity is the engine of progress. Whether you are a student, a researcher, or simply an interested observer, your questions and ideas can shape the future of artificial intelligence. The revolution belongs to all of us. The neural network revolution is not just a story of technology, but a testament to human ingenuity. As we continue to explore, invent, and dream, the boundaries of what is possible will keep expanding. The journey is far from over, and the best is yet to come.